hypotenuse. This is the base, and this is the height. So this value can be, this difference can be placed right over there. All right, so there's an angle between the maximum electromotive force that the circuit RLC circuit can have, which can be expressed in terms of the voltage drop across the resistance. All right, so the value of the electromotive force for the RLC circuit is going to be the vector sum of this plus that. All right, so base squared, which would be some r, times the square of the height, because it's a triangle, so this is going to give us the hypotenuse value. Or we can express the voltage values in terms of the current as well as the resistive terms. We'll do back substitution. And then pull out the current value, because it's the same current that's going to go through all of them. And then pull the current value out of the square root, divide both sides by the current value. All right, now everything is divided. So the voltage divided by current is going to give you the overall resistance term. That overall resistance term is going to be expressed in terms of Z. All right, this is like the total resistance of the circuit in a sense, otherwise known as impedance. The total resistance is going to be known as impedance of the circuit. It's got the units of ohms. So the total voltage or electromotive force divided by Z is going to give us the total current. All right, so impedances are related to resistance as well as the reactance terms, inductive reactance as well as the capacitive reactance terms. All right, so that's our RLC circuit. The current is going to be in phase with the voltage, obviously. Current is going to lead the voltage, because current is what charges up the capacitor. And voltage, in the case of the inductor, is going to lead the current by 90 degrees because current is a reaction to the change in voltage. So the current is going to happen in order to prevent the change in voltage within the inductor. And then we can come up with a total voltage value, obviously, for the RLC circuit, subtracting the voltage from the voltage across the inductor from the voltage across the capacitor, because these are vectors and pointing in opposite directions. And this is the voltage drop across the resistor. Immediately you can turn this into a triangle, and the total voltage value is going to be the hypotenuse. So base squared plus the height squared is going to give you the hypotenuse. So based upon everything that we discussed, the voltage across the inductor is going to lead the voltage across the capacitor by 100 milliamps. So that's what we have to look for. I think that's the case. D is the best answer. So makes sense. All right, so the impedance of an RLC circuit is definitely increased. So for that, let's just check to see what we need for that to make sense. All right, so if you want to increase the impedance of it, so let's just go further. All right, so this term is the impedance term. All right, so if you want to increase the impedance, if you increase the resistance, obviously the impedance is going to go up. If you increase the inductive reactance term, once again, the impedance is going to go up. If you increase the capacitive reactance term, impedance is going to go down. All right, so we got a bunch of options here. So let's check to see which one actually makes sense for that. So impedance of an RLC circuit is definitely increased if you increase the resistance value. Yeah, if you increase the resistance value, it's definitely going to increase it. So the best answer is going to be D in this case. All right, now let's focus on the phase angle. The phase angle is this angle that we're looking at. All right, so this is the maximum electromotive force that the circuit can have. And you're expressing it in terms of the voltage drop across the resistor. All right, so that's our phase angle. So voltage drop across the resistor. These are the voltages across the inductor as well as the capacitors. That's the maximum voltage that the circuit is going to be able to have. And this is our phase angle. All right, so we can express the phase angle, obviously. All right, moving forward, sometimes it does this. I'm not sure why. All right, so once again, we turn this into a triangle. And then this phase angle will be easy to find. This is the opposite over the adjacent, so that's going to be the tangent of the angle. Or we can express the voltages in terms of the resistive terms. that we generated from here. Voltage can be expressed in terms of the resistive terms. Solve for the angle, and that's it. All right, so that's going to give us the phase angle. All right, you may want, you will definitely need this for the test. All right, so what does it mean? Okay, so what happens to the phase angle if the voltage across the inductor and the voltage across the capacitor are the same? So the phase angle, if that's the case, is going to go to 0. And also, if the inductive reactance and the capacitive reactance terms, if they're the same, once again, the phase angle is going to go to 0. That's what happens. If the inductive reactance term is much larger than the capacitive reactance term, the phase angle is going to get much larger. If the capacitive reactance is larger than the inductive reactance, obviously it's going to be, the phase angle is going to be negative under the circumstance. It's going to be on the other side. Okay, so, and once again, just think of this in terms of the voltages across the inductor as well as capacitor. And then you have to be able to look at it also in terms of the resistance terms, inductive reactance as well as the capacitive reactance. Next one is the power. Power is how fast energy gets converted, in this case, into heat. All right, that's the way we will look at it. So that's the power lost. How fast energy gets converted into heat or light that we're looking at. All right, so we have our impedance term. So we'll express it in terms of impedance. All right, so once again, this is the power angle that we were dealing with, expressed in terms of the impedance of the circuit. So we're only interested in the amount of power lost. All right, so the resistance can be expressed in terms of the total resistance of the circuit that happens to the impedance. So obviously, this is the adjacent of the triangle, so that becomes the cosine of the angle. All right, this is cosine of the angle is known as the power factor. Now let's express this in terms of R is going to get expressed in terms of Z, the impedance. All right, so the maximum current depends on the maximum voltage divided by the total resistance of the circuit. So we'll do a back substitution. And I want you to notice that this Z squared, and you got Z, so there's going to be a cancellation between those two. As a result, this is the maximum electromotive force squared divided by Z times the cosine of the angle. That's it. So that's your power that we're looking at. So the power is being expressed in this case in terms of impedance, so that's the total resistance. All right, so that's the square of the total voltage divided by the total resistance of the circuit, which is the impedance times the cosine of the angle, the power factor itself. And that's it. All right, so the rate of heat dissipation in an AC circuit with resistance and the effective current is given by maximize whenever the impedance value is minimized. So how do we minimize the impedance value? Well, impedance is going to be a combination of resistance as well as capacitive, as well as the inductive reactance values. So what we need to do is we need to make the denominator smaller. And the denominator is going to have its minimum value when these two terms are equal to each other. So inductive reactance and the capacitive reactance terms are the same. So when they're equal to each other, obviously this term drops out. Under the circumstances, the Z impedance becomes minimum, or it becomes minimized. So the question is, at what frequency? Which frequency is going to minimize the impedance? So resonance is going to happen at what frequency? So that's what we're interested in. So solve for omega, and then express omega in terms of the linear frequency, and isolate that. That's it. All right, so this gives us the resonant frequency. So resonance is going to happen. At resonance, what happens is the current is maximized. And resonance happens when the impedance reaches its lowest value. And that happens at its resonant frequency, which is denoted in terms of half hour.
But no matter how precise the analogy, differences can arise. For example, when resonance occurs in electrical oscillators, it seldom lets people down. But when resonance occurs in mechanical oscillators, things can get out of hand. In electric circuits, resistance can help keep things from getting out of hand. For example, consider a capacitor and a resistor in an AC circuit. If the frequency is low enough, the charging and discharging of the capacitor can keep up with the oscillating applied voltage. But at higher frequency, the capacitor can't charge and discharge fast enough, so no voltage difference develops across it, and nearly all the voltage is across the resistor. On the other hand, if an inductor is in the circuit, at low frequency, there's plenty of time to build up current in it without much voltage across it. But at higher frequency, the current in the inductor can't change fast enough before it has to turn around. So the voltage is mostly across the inductor, and there's not much left across the resistor. When all the elements are in the same circuit at low frequency, most of the voltage goes into charging and discharging the capacitor. At higher frequency, more of the voltage is used up trying to change the current in the inductor. In fact, at very high frequency, the inductor virtually keeps any current from flowing at all. But if the frequency is just right, in other words, at the resonant frequency, a quite large current flows. The capacitor charges and discharges. Current builds up and reverses in the inductor, and the resistor burns up enough energy to keep the oscillations under control.
All right, so we got the RLC circuit. Frequency and capacitive reactance. As the frequency starts to go up, notice that the capacitive impedance, capacitive reactance starts to go down, which means that it starts to act like a short circuit, as if there's nothing there. I mean, if you keep reversing the direction so fast, it doesn't really get a chance to build up. The charge doesn't get a chance to build up that often, and then it's going to look like the capacitor is not there, so it's not going to offer a lot of impedance. All right, so at extremely high frequencies, the capacitive reactance is not a problem, but at extremely low frequencies, it's going to offer a lot of resistance in the sense that the charge is going to build up and it's going to get discharged. So the charge builds up and discharges and builds up, discharges again. All right, so this is what happens at extremely low frequencies. So at extremely low frequencies, the capacitor is going to dominate. It's going to act more like a resistor. That's what it means. All right. At extremely high frequencies, if you're looking at an inductor, more often you change the direction of the current and the value of the current, more it's going to resist. So it's going to start to act like an extremely resistive component. So the inductor is going to dominate in this region where the resonance takes place. I'm having a really tough time to come up with a better explanation than that, aside from this one, because this is the one that we're looking at. All right, so the current is going to become maximized at minimum impedance. And at that point, the only dominant term which is left is that term. All right, so right at that point, the capacitive reactance and the inductive reactance terms are the same. That's what it means. All right, so the best answer is the capacitor acts like a short circuit at high frequencies. And the inductor acts like a short circuit at low frequencies. All right, so what does that mean? So what that means is at high frequencies, it's going to act like a short circuit as if there's nothing there, because you're turning the current run so often, so fast and so often that the capacitor doesn't matter. And extremely low frequencies, inductor is not going to offer a lot of resistance to changing current. All right, so nothing happens here. All right, so the resonance is going to happen when the capacitive reactance equals. So C is the best answer for that one. So we got the RLC circuits, application metals. All right, I'm going to put the PowerPoint up at some point. So this is the problem that I want you to focus on when you're studying for the task.